workers of the world unite. You have nothing to lose but your ignorance about classes, which are a means of bundling data and functionality together. Creating a new class creates a new type of object, allowing new instances of that type to be made. Each class instance can have attributes attached to it for maintaining its state. Class instances can also have methods defined by its class for modifying its state. Compared with other programming languages, Python's class mechanism adds classes with a minimum of new syntax and semantics. It is a mixture of the class mechanisms found in C++ and Modula 3, which I've never heard of. Python classes provide all the standard features of object-oriented programming. The class inheritance mechanism allows multiple base classes. A derived class can override any methods of its base class or classes, and a method can call the method of a base class with the same name. Objects can contain arbitrary amounts and kinds of data. As is true for modules, classes partake of the dynamic nature of Python. They are created at runtime and can be modified further after creation. In C++ terminology, normally class members, including the data members, are public, except see below private variables, and all member functions are virtual. As in Modula 3, there are no shorthands for referencing the object's members from its methods. The method function is declared with an explicit first argument representing the object itself, which is provided implicitly by the call. As in Smalltalk, classes themselves are objects. This provides semantics for importing and renaming. Unlike C++ and Modula 3, built-in types can be used as base classes for extension by the user. Also, like in C++, most built-in operators with special syntax, arithmetic operators, subscripting, etc., can be redefined for class instances. Now, the author states, lacking universally accepted terminology, to talk about classes, I will make occasional use of Smalltalk and C++ terms. I would use Modula 3 terms, since its object-oriented semantics are closer to those of Python than C++, but I expect a few readers have heard of it. Good expectation. A word about names and objects. Objects have individuality, and multiple names in multiple scopes can be bound to the same object. This is known as aliasing in other languages, when multiple things point to the same spot in computer memory. This is usually not appreciated on a first glance at Python, and can be safely ignored when dealing with immutable basic types, such as numbers, strings, and tuples. However, aliasing has a possibly surprising effect on the semantics of Python code involving mutable objects, such as lists, dictionaries, and most other types. This is usually used to the benefit of the program, since aliases behave like pointers in some respects. For example, passing an object is cheap, since only a pointer is passed by the implementation, and if a function modifies an object passed as an argument, the caller will see the change. This eliminates the need for two different argument passing mechanisms as in Pascal. Python scopes and namespaces. Before introducing classes, I first have to tell you something about Python's scope rules. Class definitions play some neat tricks with namespaces, and you need to know how scopes and namespaces work to fully understand what's going on. Incidentally, knowledge about this subject is useful for any advanced Python programmer. Let's begin with some definitions. A namespace is a mapping from names to objects. Most namespaces are currently implemented as Python dictionaries, but that's normally not noticeable in any way except for performance, and it may change in the future. Examples of namespaces are the set of built-in names containing functions such as abs and built-in exception names, the global names in a given module, and the local names in a function invocation. So it's worked from larger to smaller and smaller namespaces here. In a sense, the set of attributes of an object also form a namespace. The important thing to know about namespaces is that there is absolutely no relation between names in different namespaces. That's why they call it a namespace. For instance, two different modules may both define a function called maximize without there being any confusion. Users of the modules must prefix it with the module name to differentiate between the two things, both given the same name, maximize. By the way, I use the word attribute for any name following a dot. For example, in the expression z.real, real is an attribute of the object z. Strictly speaking, references to names in modules are attribute references. In the expression modName.funcName, modName is a module object and funcName is an attribute of it. In this case, there happens to be a straightforward mapping between the module's attributes and the global names defined in the module. They share the same namespace. Attributes may be read-only or writable. In the latter case, assignment to attributes is possible. Module attributes are writable. You can write modName.the_answer equals 42. Writable because it has to be always. Writable attributes may also be deleted with the del statement. For example, del modName.the_answer will remove the attribute the answer from the object named by modName. It's not deleting modName. Namespaces are created at different moments and have different lifetimes. The namespace containing the built-in names is created when the Python interpreter starts up and is never deleted. The global namespace for a module is created when the module definition is read in. Normally, module namespaces also last until the interpreter quits. The statements executed by the top-level invocation of the interpreter, either read from a script file or interactively, are considered part of a module called __main__. So they have their own global namespace. And the built-in names actually also live in a module that's just called built-ins. Just all that is kind of under the hood. You have to look for it to see it. The local namespace for a function is created when the function is called and deleted when the function returns or raises an exception that is not handled within the function. And actually forgetting would be a better way to describe what actually happens than delete. Of course, recursive invocations each have their own local namespace. A scope is a textual region of a Python program where a namespace is directly accessible. And directly accessible here means that an unqualified reference to a name attempts to find the name in the namespace. Although scopes are determined statically, they are used dynamically. At any time during execution, there are 3 or 4 nested scopes whose namespaces are directly accessible. The innermost scope, which is searched first, contains the local names. The scopes of any enclosing functions, which are searched starting with the nearest enclosing scope, contain non-local but also non-global names. And the next to last scope contains the current module's global names. The outermost scope, searched last, is the namespace containing built-in names. If a name is declared global, then all references and assignments go directly to the next to last scope containing the module's global names. To rebind variables found outside of the innermost scope, the non-local statement can be used. If not declared non-local, those variables are read-only. An attempt to write to such a variable will simply create a new local variable in the innermost scope, leaving the identically named outer variable unchanged. Usually, the local scope references the local names of the textually current function. Outside functions, the local scope references the same namespace as the global scope, the module's namespace. Class definitions place yet another namespace in the local scope. It is important to realize that scopes are determined textually. The global scope of a function defined in a module is that module's namespace, no matter from where or by what alias the function is called. On the other hand, the actual search for names is done dynamically at runtime. However, the language definition is evolving towards static name resolution at compile time. So don't rely on dynamic name resolution. In fact, local variables are already determined statically. A special quirk of Python is that if no global or non-local statement is in effect, assignments to names always go into the innermost scope. Assignments do not copy data, they just bind names to objects. The same is true for deletions. The statement del x removes the binding of x from the namespace referenced by the local scope. In fact, all operations that introduce new names use the local scope. In particular, import statements and function definitions bind the module or function name into the local scope. The global statement can be used to indicate that particular variables live in the global scope and should be rebound there. You can specify that by just actually writing global beforehand. The non-local statement indicates that particular variables live in an enclosing scope and should be rebound there. Scopes and namespaces example. So this is an example demonstrating how to reference the different scopes and namespaces and how global and non-local affect variable binding. It's kind of an interesting little thing here with a slightly unexpected outcome. We've got the function scope test, in the definition of which we've got three other functions defined: do local, do non-local, and do global. And all of these attempt to update the value of a variable with the same name, spam. In the first one, it's just spam equals local spam. In do non-local, they use the non-local statement first. And in do global, they use the global statement first. And then do the same thing, trying to update the value of this same named variable. And then we update the value of it outside these function definitions, just within this one. And finally, this function scope test calls the functions do local, do non-local, and do global. And after each one, prints a little message along with that variable spam to show us at every step of the process what will actually happen to the variable spam because of these statements. And you might be, think about try and predict what the output would be, because it's a little bit, you might find it's not what you were expecting. After local assignment, so we actually get test spam. None of these messages. It's this one first. After non-local assignment, because the non-local statement was used, even though the value of spam was updated within the definition of this function, which was within the definition of this one, because the non-local statement was used, then the value set to spam continues to be what is referenced whenever spam is called, even outside this function, but still within this one. It's non-local. And now, after do global, whenever the global statement is used, this updated value of spam is actually only relevant to the global namespace, the module itself. And so, even after, within this function definition, even after we call the do global function and print spam after that, it doesn't say global spam. The hell? It says non-local spam. Because this global statement affects spam in a namespace outside of the function scope test, and it's not relevant until we see, after all the function definition of scope test, after we call that function scope test, when finally we call the print function for spam completely outside of all this, that's when we see global spam. Okay. Might just pause and look at this a little bit in more detail. It was a quick covering it. Note how the local assignment, which is default, didn't change scope test's binding of spam. The non-local assignment changed scope test's binding of spam, and the global assignment changed the module level binding. You can also see that there was no previous binding for spam before the global assignment. Outside of the function scope test, spam hadn't been defined as anything yet, until within the function scope test, because the global statement was used. That definition affected spam even outside of the function scope test. A first look at classes. Classes introduce a little bit of new syntax, 3 new object types, and some new semantics. Class definition syntax. The simplest form of class definition looks like this. The word class, followed by the class name, which is typically by convention written in title case like this, the first letter of each word being capitalized. And then you got your various statements. Class definitions, like function definitions, def statements, must be executed before they have any effect. You could conceivably place a class definition in a branch of an if statement or inside a function. In practice, the statements inside a class definition will usually be function definitions, but other statements are allowed, and sometimes useful. We'll come back to this later. The function definitions inside a class normally have a peculiar form of argument list, dictated by the calling conventions for methods. Again, this is explained later. When a class definition is entered, a new namespace is created and used as the local scope. Thus, all assignments to local variables go into this new namespace. In particular, function definitions bind the name of the new function here. When a class definition is left normally, via the end, a class object is created. This is basically a wrapper around the contents of the namespace created by the class definition. We'll learn more about class objects in the next section. The original local scope, the one in effect just before the class definition was entered, is reinstated, and the class object is bound here to the class name given in the class definition header, which in the example was class name. Class objects. Class objects support 2 kinds of operations: attribute references and instantiation. Attribute references use the standard syntax used for all attribute references in Python, object.name. Valid attribute names are all the names that were in the class's namespace when the class object was created. So if the class definition looked like this, class, my class, the docstring stating a simple example class, and the variable I set at the value of 12,345, and a definition of a function called f, which takes in the one inevitable conventional argument self, or parameter self, and returns hello world, then myClass.I and myClass.f are valid attribute references, returning an integer and a function object respectively. Class attributes can also be assigned to, so you can change the value of myClass.I by assignment, like the setting the value of a variable like usual. Underscore underscore doc underscore underscore is also a valid attribute, returning the doc string belonging to the class, the string that said a simple example class. Class instantiation uses function notation. Just pretend that the class object is a parameterless function that returns a new instance of the class. For example, assuming the above class. If we could make a variable x and set it equal to simply my class with nothing passed in as argument, and this will make an instance of, it will instantiate my class. It will create a new instance of the class and assign that object to the local variable x. So the instantiation operation, colon, a class object, creates an empty object. Many classes like to create objects with instances customized to a specific initial state. Therefore, a class may define a special method named underscore underscore init underscore underscore opening and closing parentheses, or the init method, which is defined like a regular function. It has the one parameter self at least and sets self.data equal to an empty list in this example. When a class defines an init method, an initialization method, class instantiation automatically invokes init for the newly created class instance. So each time that you create a new instance of that class, it will automatically invoke whatever is defined as the init method in the class definition. It's like a set of basic instructions that must be carried out for any unique particular object in this overarching template or category that is a class. At any time you make a specific unique instance of that class, it must come along with running out or carrying out the init instructions. What? Okay, so in this example, a new initialized instance can be obtained by doing this. Did I already say? I already said this. What? No? They just already said it. Okay. Of course, the init method may have arguments for greater flexibility. In that case, arguments given to the class instantiation operator are passed on to init. For example, say we defined a class complex, and in the init method we define it with 3 parameters. First, its typical self, and then the additional real part and imaginary part. And we set whatever is passed into real part, we connect to self.r, and whatever is passed into image part, we connect to self.i, we assign to. And so if later we create an instance of the complex class by creating a variable x and setting it equal to the value of calling the class name together with these 2 optional arguments that we created, or the parameters, right? We pass in as arguments here these 2 numbers, and then after that we can refer to them with variable name .r and variable name .i, and it will be the arguments passed in, right? And so this would output 3.0, comma, negative 4.5. Instance objects. Now what can we do with instance objects? The only operations understood by instance objects are attribute references. There are 2 kinds of valid attribute names, data attributes and methods. Data attributes correspond to instance variables in Smalltalk, whoosh, and data members in C++, whoosh. Data attributes need not be declared. Like local variables, they spring into existence when they are first assigned to. For example, if x is the instance of my class created above, the following piece of code will print the value 16 without leaving a trace. We can set x.counter equal to 1, and while x.counter is less than 10, we will update the value of x.counter to equal x.counter multiplied by 2. And we'll print x.counter, and we can delete x.counter, and all this, what this will do, we'll print 16 and then be gone. The other kind of instance attribute reference is a method. A method is a function that belongs to an object. In Python, the term method is not unique to class instances. Other object types can have methods as well, as we have covered list methods, for example. Oh my god, that's what it... I swear that wasn't intentional. For example, list objects have methods called append, insert, remove, sort, and so on. However, in the following discussion, we'll use the term method exclusively to mean methods of class instance objects, unless explicitly stated otherwise. Valid method names of an instance object depend on its class. By definition, all attributes of a class that are function objects define corresponding methods of its instances. So in our example, x.f is a valid method reference since myClass.f is a function, but x.I is not since myClass.I is not. But x.f is not the same thing as myClass.f. It is a method object, not a function object. Method objects. By the way, if this is a little confusing, again, don't feel bad about that. It's a little bit confusing. Usually, a method is called right after it is bound. So say x.f, opening and closing parentheses. In the myClass example, this will return the string hello world. However, it is not necessary to call a method right away. x.f is a method object and can be stored away and called at a later time. For example, say we created a variable xf that we set equal to the value of x.f. And then we have a while true that will print xf, and just an empty parenthetical statement, right? And this will continue to print hello world until the end of time. It is not programming best practices to create infinite loops. What exactly happens when a method is called? You may have noticed that x.f was called without an argument above, even though the function definition for f specified an argument. What happened to the argument? Surely, Python raises an exception when a function that requires an argument is called without any, even if the argument isn't actually used. Actually, you may have guessed the answer, or you may not have. Don't feel bad if you didn't. The special thing about methods is that the instance object is passed as the first argument of the function. The instance object is passed as the first argument of the function. In our example, the call x.f is exactly equivalent to myClass.f with x passed in as argument. Let that sink in. In general, calling a method with a list of n arguments is equivalent to calling the corresponding function with an argument list that is created by inserting the method's instance object before the first argument. In general, methods work as follows. When a non-data attribute of an instance is referenced, the instance's class is searched. If the name denotes a valid class attribute that is a function object, references to both the instance object and the function object are packed into a method object. When the method object is called with an argument list, a new argument list is constructed from the instance object and that argument list, and the function object is called with this new argument list. Class and instance variables. Generally speaking, instance variables are for data unique to each instance, and class variables are for attributes and methods shared by all instances of the class. Instance variables are data unique to each instance. Class variables for attributes and methods shared by any and all instances of the class, now or future. Okay, so say, generally speaking, oh no, I'm sorry, I started over. Say we made a class called dog. Okay, in the class definition, we set the variable kind equal to the string canine. This is a class variable that will be shared by all instances, whatever class objects we make in the future out of this class dog. Within them, the variable kind will be set equal to canine. Okay, and then the init method is defined within the class definition, which takes in, as always, the instance object as argument and name. And we set self.name, that is the instance that we're creating. Whenever we create an instance of this class, that's what self is referring to, right? That we set the name of that instance equal to the variable name that was, okay, and that is an instance variable that will be unique to each instance, because name will equal whatever argument we pass in, making that individual instance. Okay. So if after this class is defined, we create a variable d and make it an instance of the dog class that takes in the argument Fido because you don't have to pass anything into self, remember, because it refers to the instance itself. This will be passing in here at this spot. And we make another E that is is an instance of the dog class into which we have passed buddy as name. Then if we call d.kind, which is shared by all of them, then we'll see canine. If we call e.kind, we'll also see canine. But if we call d.name, we will see Fido, and if we call e.name, we will see buddy, because those are unique to those instances. As discussed in a word about names and objects, shared data can have possibly surprising effects with involving mutable objects such as lists and dictionaries. For example, the tricks list in the following code should not be used as a class variable, because just a single list would be shared by all dog instances. All dogs share a list. I loved that movie when I was a kid. Stupid. Okay, so we define dog again. We're starting over. We're making this class. We're trying again. Make this class dog. And we've got an empty list in it. Tricks. This is a mistake. Okay. Because here we got this setup is just like earlier, but within this class we've also defined the function add_trick, which takes in the instance itself and a custom trick, and then it tries to append whatever is passed in as argument to trick to the end of the empty list, tricks. But because tricks, the empty list, is a class variable, this means that every time that we make any new instance of this, it is adding more and more and more tricks to this one list. So it'll work like earlier when passing in the name, making an instance of the dog, D, make another instance of the dog class, E, and we pass in unique names to each one. But when we try to do the same thing, passing in unique tricks using our add_trick method, if we call either one of those, we will see both tricks that have been passed in. So, correct design of the class should use an instance variable instead and make the empty list in the init method in this case, which will create a new empty list for each dog, so that when this is used, it will only be attached to each unique instance of the class. Now we see D's trick is roll over and E's trick is play dead. Random remarks. Baba Booty. If the same attribute name occurs in both an instance and in a class, then attribute lookup prioritizes the instance. It always kind of starts at the smallest, closest area and then goes expanding outwards. So, say we make a warehouse class. In it we set purpose equal to the string storage, region equal to the string west. Now if we make an instance of that class called W1, and then we try to print the purpose and the region of W1, we get storage west. We make a new instance called W2 of the same class, and here we set the .region method or attribute. I'm still confused as to when to use which, but you know what I'm saying. We set that equal to east. Now, if we print this instance's purpose and region, purpose remains unchanged, but the region is unique, changed to what we passed in specifically to that instance. Data attributes may be referenced by methods as well as by ordinary users, clients, of an object. In other words, classes are not usable to implement pure abstract data types. In fact, nothing in Python makes it possible to enforce data hiding. It is all based upon convention. On the other hand, the Python implementation written in C can completely hide implementation details and control access to an object if necessary. This can be used by extensions to Python written in C. I guess in case you didn't know, like the basic default, the Python interpreter, and it's all written in the C programming language. It's a more lower level, which I need to get around to learning that now. Clients should use data attributes with care. Clients may mess up invariants maintained by the methods by stamping on their data attributes. Note that clients may add data attributes of their own to an instance object without affecting the validity of the methods, as long as name conflicts are avoided. Again, a naming convention can save a lot of headaches here. There is no shorthand for referencing data attributes or other methods from within methods. I find that this actually increases the readability of methods. There is no chance of confusing local variables and instance variables when glancing through a method. Often, the first argument of a method is called self. This is nothing more than a convention. Just like, for I in range 10, you could just say for Jim in range 10, it would make no difference. It's the same, that first self argument is just, people call it that by convention. You should do that, obviously, though. The name self has absolutely no special meaning to Python. Note, however, that by not following the convention, your code may be less readable to other Python programmers, and it is also conceivable that a class browser program might be written that relies upon such a convention. There's literally no benefit to not following the convention, so any function object that is a class attribute defines a method for instances of that class. It is not necessary that the function definition is textually enclosed in the class definition. Assigning a function object to a local variable in the class is also okay. So you could first define the function, as I have in this example, f1, and this is outside of the class definition, but within the class definition, you just have to set a local variable f equal to the previously defined function here. It'll be just the same as if you define that function within the class definition. Now, fg and h are all attributes of class C that refer to function objects, and consequently they are all methods of instances of C. H being exactly equivalent to G. Note that this practice usually only serves to confuse the reader of a program. Methods may call other methods by using method attributes of the self argument. So say we made a class bag, and we define the init method, defined add, and we defined add twice. Okay, and in the init method, we set we set self.data equal to an empty list. There's no... Wait a second. Okay, right. Got confused for a second there. The init method creates an empty list, data, self.data. Then, after that, the add function defined within the same class will append what is passed in as x to the data to this list. And then the add twice function affects the thing made here, right? Using these methods, the self.dot methods. Methods may reference global names in the same way as ordinary functions. The global scope associated with a method is the module containing its definition. So a class is never used as a global scope. While one rarely encounters a good reason for using global data in a method, there are many legitimate uses of the global scope. For one thing, functions and modules imported into the global scope can be used by methods as well as functions and classes defined in it. Usually, the class containing the method is itself defined in this global scope, and in the next section we'll find some good reasons why a method would want to reference its own class. each value is an object and therefore has a class, also called its type. It is stored as object.__class__. Inheritance. Of course, a language feature would not be worthy of the name class without supporting inheritance. It's kind of the key concept. The syntax for a derived class definition looks like this. It's exactly the same as just defining a class, except it does take as argument, or as a parameter, the base class name, the thing that is deriving from, or that it is inheriting from. The name base class name must be defined in a namespace accessible from the scope containing the derived class definition, of course. In place of a base class name, other arbitrary expressions are also allowed. This can be useful, for example, when the base class is defined in another module. So this would be here, it's exactly like this, except we're assuming that base class was defined in a separate module. So first you put the module name dot base class name. Execution of a derived class definition proceeds the same as for a base class. When the class object is constructed, the base class is remembered. This is used for resolving attribute references. If a requested attribute is not found in the class, the search proceeds to look in the base class. This rule is applied recursively if the base class itself is derived from some other class. There's nothing special about instantiation of derived classes. Derived class name creates a new instance of the class. Method references are resolved as follows. The corresponding class attribute is searched, descending down the chain of base classes if necessary, and the method reference is valid if this yields a function object. Derived classes may override methods of their base classes. Because methods have no special privileges when calling other methods of the same object, a method of a base class that calls another method defined in the same base class may end up calling a method of a derived class that overrides it. For C++ programmers, all methods in Python are effectively virtual. An overriding method in a derived class may in fact want to extend rather than simply replace the base class method of the same name. There is a simple way to call the base class method directly. Just call base class name dot method name with self, arguments. This is occasionally useful to clients as well. Note that this only works if the base class is acceptable as base class name in the global scope. Python has two built-in functions that work with inheritance. Use isInstance to check an instance's type. So isInstance, the object name, int, will be true only if the object dot underscore underscore class underscore underscore is an integer data type or some class derived from int. Use isSubclass to check class inheritance. So isSubclass bool, int is true since bool is a subclass of int. However, isSubclass float int is false, since float is not a subclass of int. Multiple inheritance. Python supports a form of multiple inheritance as well. A class definition with multiple base classes looks like this. Class, derived class name. Base 1, base 2, base 3. Okay. For most purposes, in the simplest cases, you can think of the search for attributes inherited from a parent class as depth first, left to right, not searching twice in the same class where there is an overlap in the hierarchy. Thus, if an attribute is not found in derived class name, it is searched for in base 1, then, recursively, in the base classes of base 1, and if it was not found there, it was searched for in base 2, etc., etc. In fact, it is slightly more complex than that. The method resolution order changes dynamically to support cooperative calls to super. This approach is known in some other multiple inheritance languages as call next method, and is more powerful than the supercall found in single inheritance languages. Not sure what any of that means yet. Dynamic ordering is necessary because all cases of multiple inheritance exhibit one or more diamond relationships, where at least one of the parent classes can be accessed through multiple paths from the bottommost class. For example, all classes inherit from object, so any case of multiple inheritance provides more than one path to reach object. To keep the base classes from being accessed more than once, the dynamic algorithm linearizes the search order in a way that preserves the left-to-right ordering specified in each class, that calls each parent only once, and that is monotonic, meaning that a class can be subclassed without affecting the precedence order of its parents. Taken together, these properties make it possible to design reliable and extensible classes with multiple inheritance. For more details, see the Python 2.3 method resolution order. Private variables. Private instance variables that cannot be accessed except from inside an object don't exist in Python, so they cannot hurt you. However, there is a convention that is followed by most Python code. A name prefixed with an underscore, e.g. underscore spam, should be treated as a non-public part of the API, whether it is a function, a method, or a data member. It should be considered an implementation detail and subject to change without notice. Since there is a valid use case for class private members, namely to avoid name clashes of names with names defined by subclasses, there is limited support for such a mechanism, called name mangling. Any identifier of the form underscore underscore spam, at least 2 leading underscores, at most 1 trailing underscore, is textually replaced with underscore class name underscore underscore spam, where class name is the current class name with leading underscores stripped. This mangling is done without regard to the syntactic position of the identifier, as long as it occurs within the definition of a class. Name mangling is helpful for letting subclasses override methods without breaking intra-class method calls. For example, and intra means within, right? Like that it's, as opposed to like inter, is across, but intra is anything within the class. For example, say we made a class called mapping, what the hell, why won't this, okay. We define the init method to take self and an iterable. We make an items list attached to the instance, to whatever instance of mapping we make as an empty list called items list. We make this mangled update, which takes an iterable attached to any instance of the class mapping that we create. Define the function update, which takes self and iterable, and for item in iterable, it will append item to our empty list items list. And here we have underscore underscore update set equal to update, and this is a private copy of the original update method. Then if we make another class, mapping subclass, which inherits from, mapping, we define the update function, take in self keys and values, provides new signature for update, but does not break the init method. For item in the zip of keys and values passed in, we'll append that item to items list, and everything is going to be groovy. The above example would work even if mapping subclass were to introduce an underscore underscore update identifier, since it is replaced with underscore mapping underscore underscore update in the mapping class, and underscore mapping subclass underscore underscore update in the mapping subclass class, respectively. Note that the mangling rules are designed mostly to avoid accidents. It still is possible to access or modify a variable that is considered private. This can even be useful in special circumstances, such as in the debugger. Notice that code passed to exec or eval, does not consider the class name of the invoking class to be the current class. This is similar to the effect of the global statement, the effect of which is likewise restricted to code that is byte compiled together. The same restriction applies to getAttribute, setAttribute, and deleteAttribute, as well as when referencing the dunder dict directly. Odds and ends. Sometimes it is useful to have a data type similar to the Pascal record or C struct, bundling together a few named data items. The idiomatic approach is to use data classes for this purpose. So, we could import, or we could, from the module data classes, import data class. Then we put the data class decorator on this class employee, and we can define name as being a string data type, department as being a string data type, and salary being an integer data type. Oh, whoops, my laptop's dying. And then, if we want to make an instance of the employee class called John, and we pass in the string John, the string computer lab, and the integer 1000, then we can ask to see the dept attribute of this instance, and it'll return the string computer lab, because we've defined that, right? And John.salary will be 1000. Now, a piece of Python code that expects a particular abstract data type can often be passed a class that emulates the methods of that data type instead. For instance, if you have a function that formats some data from a file object, you can define a class with methods read and readLine that get the data from a string buffer instead and pass it as an argument. Instance method objects have attributes too. The dunder self is the instance object with the method im, and the dunder func is the function object corresponding to the method. A little bit lost there. Iterators. By now, you have probably noticed that most container objects can be looped over using a for statement, such as for element in a list containing 3 elements, print the element. For element in a tuple containing 3 elements, print element. For key in a dictionary containing 2 items, 2 key value pairs, you can print key. For character in a string containing 3 characters, you can print character. For line in the result of passing in a text file to the open function, you can print line. Okay, this style of access is clear, concise, and convenient, and cool. The use of iterators pervades and unifies Python. Behind the scenes, the for statement calls iter on the container object. The function returns an iterator object that defines the method __next__, which accesses elements in the container one at a time. When there are no more elements, next raises a stop iteration exception which tells the for loop to terminate. You can call the next method using the next built-in function. In this example, shows how it all works. Let's say we set the value of a variable s equal to the string abc, and we set the value of the variable it equal to the result of passing in s to iter, the container object, into iter. And this will, if we ask to see what it is now, then we see that a iterator object has been created. Okay, and if we pass this iterator object into next 3 times, we will iterate through. It'll return one at a time the characters in it, right? A, then we call next B, next C, next it, and since there are only 3 steps, finally it will raise a stop iteration exception if we continue calling it. Having seen the mechanics behind the iterator protocol, it is easy to add iterator behavior to your classes. Define an iter method which returns an object with a next method. If the class defines next, then iter can just return self. So say we have a class called reverse. The docstring explains it's an iterator for looping over a sequence backwards. The init method will refer to the instance created and takes in data as an argument. And then it will bind or assign the data passed in to the instance, and it will create index, which will be the result of passing in data to the length function. Defining the iterator will just return itself. And next, if self.index equals 0, then raise stop iteration. If self.index equals self.index minus 1, so you know, if 0 minus 1 is the very last one, right? Then return self.data at the index number that would be self.index. So that would result in it starting at the end and iterating through just like this iterated next at the first character one at a time forward. This reverses that. So say we created rev, an instance of the class reverse into which we passed spam again. Now if we pass this instance into the iter, we see a main.reverse object, and for char in rev, we iterate through it, print character, then we will see the last character first up to the character at index 0, at which point the stop iteration is raised. Generators. Generators are a simple and powerful tool for creating iterators. They are written like regular functions but use the yield statement whenever they want to return data. Not return, yield. It's one of the hallmarks of a generator. Each time next is called on it, the generator resumes where it left off. It remembers all the data values and which statement was last executed, and no further. Right? That's why it's called a generator, is it will generate the value when you call it, one step at a time. And it's a way of like saving memory and stuff. You don't have to store an entire list. If you've got like the rules that would define everything in the list, then you can just use a generator and just go step by step to find something within this list. An example shows that generators can be trivially easy to create. Say, like this. Because we used yield. For char in reverse with golf passed in, print char, we'll get the same result. Anything that can be done with generators can also be done with class-based iterators, as described in the previous section. What makes generators so compact is that the underscore, iter, and the _next methods are created automatically. So let's take another little quick look at it. We had to specifically create these things here. But as far as I understand it, it's literally because you use the yield word. That's kind of it. The yield statement is what defined it as a generator. You can just use these built-in functions, length and range, together with yield, yielding data at the given index. That's all you gotta do. Sorry, that doesn't really clarify it, that explanation. I'm just not sure how to clarify it any further than that. I'm also tired. Where the hell am I? Is that? Yeah, okay. Another key feature is that the local variables and execution state are automatically saved between calls. This made the function easier to write and much more clear than an approach using instance variables like self.index and self.data. In addition to automatic method creation and saving program state, when generators terminate, they automatically raise stop iteration. In combination, these features make it easy to create iterators with no more effort than writing a regular function. Generator expressions. Some simple generators can be coded succinctly as expressions using a syntax similar to list comprehensions but with parentheses instead of square brackets. These expressions are designed for situations where the generator is used right away by an enclosing function. Generator expressions are more compact but less versatile than full generator definitions and tend to be more memory friendly than equivalent list comprehensions. For example, say we write out the sum of I times I, and much like list, in a list comprehension, right? Like the sum of applying this operation for each step along this range will produce 285. And say we got x vector set equal to this list, y vector set equal to this list, that has three coordinate points. Sum of x times y for x comma y in the zip of xvec dot yvec, or the result of passing in these two variables to the zip function. This will return the dot product, 260. And the difference here is, like, it's not creating the entire list of squares like this, for instance. It's not making a list of square numbers in range 0 through 9. It is just one step at a time going through those, and this final output is all that is kept at all by that process. And you don't have to have a big list full of squares in order to generate it. And so we set unique words equal to the consequence of passing all this into the set function. Word for line in page for word in line dot split. This nested two for loops. And valedictorian we set equal to passing in student.gpa, student.name for student in graduates to max function. And we set data equal to golf. And finally, we pass all this into the list function. Data at index I for I in range of the length of the string data, -1, -1, -1, will produce flog. Like, this is that reversing thing that they made earlier, right? So this one single line could replace quite a bit of other code that I can't find anymore. Thank God. That's the end of the module, though. Except for one thing. Module objects have a secret read-only attribute called the dunder dict, which returns the dictionary used to implement the module's namespace. The name dunder dict is an attribute but not a global name. Obviously, using this violates the abstraction of namespace implementation and should be restricted to things like post-mortem debuggers. Bada bing bada boom.